Hello class, and thank you for watching this video on 6.5 properties of logarithmic functions. We're going to begin with, in this first half, or in this first part of this video, we're going to talk about the product and quotient rule of logs, and how to use those rules to expand or condense logarithmic functions. Now, the first rule is called the product rule. The product rule states that the logarithm of a product is the sum of the logs. So if I have a log of a base b and I'm multiplying two things as my input, then that could be expanded to the log base b of m plus the log base b of n. Therefore, these two properties, therefore this property can help us again expand this value, and we say that this is expanding, so we expand this value here expand this to give the product of these two things its own log. I wouldn't say it's distributing, but it's very similar to your exponential properties, where if I am multiplying two powers, like x to the power of n times x to the power of m, how I add those exponents together. So very similar again to this exponential property, but for logs. Well, let's put it in play. Like, let's see how this works. Okay, so like in this example right here, I have the log base 4 of 16x. What I can do using this property is, because I'm multiplying 16 with x, I can expand this and give this 16 its own log base 4 and give the variable x its own log base 4. So I can expand this and write this as a sum of the product, the log of the product of these two things. Now, why is this useful? The usefulness of using this property is because it lets us, again, evaluate logarithmic functions. Like in this example now, because I'm adding this value to this actually has a numerical value. The log base 4 of 16, well, that's going to be 4 to some power to equal to 16, and the answer to that is the number 2. So that means that this value is 2. So this is 2 plus the log base 4 of x. So we can use this property in order to evaluate and actually simplify and write this thing again as a vertical translation. So the usefulness of this property is to create equivalent forms of this idea here and creating, again, vertical translations to our logarithmic function. So like in this example right here, we could do the same idea. This is the common log base 10 of 10 times x. So I can expand this as the common log of 10 plus the common log of x. And just like before, I can write this and evaluate that. And since the common log of 10 is 1, because again our base is 10, 10 has to be raised to an exponent to equal to that value, to the input value of 10, which is the number 1. So that means this is going to become 1 plus the common log of x. So let's look at the graph of this last one. So we have y is equal to 10 times, or the common log of 10 times x, as you see right here. I have written it right there. And that looks like this graph right here, okay? Now, compare it to the original graph of just y is equal to x. So notice that it doesn't look obviously the same. And the usefulness of this property, and by applying this property where we can evaluate this, we can create transformations and visualize this as a vertical shift of this function. Notice that we have y of 10 of x, which is this one right here, and the original one like this. Notice how this point has been moved up to this location there. Let me plot that point, which is at 1, which is at the point 1, 1. So that's that point right there, okay? Like I said, the usefulness of this property is that instead of trying to do a vertical dilation, or in this case a horizontal dilation, and trying to recall, okay, how is this going to affect the x values or the y values, anything like that, by using this property, I can overlook any type of horizontal dilation and instead visualize this as a vertical shift, as what we talked about in graphing from the previous lesson. And because these two graphs are the same, let me, again, here's the red one, and here's this one, 1 plus log of x. By rewriting this log base, the common log of 10x as 1 plus the log of x, we get a better idea of understanding what this function is doing. It's resulting in essentially a vertical shift of the original function of the common log of x. It moves again this point to 1 unit higher along with all the other points. And if I look at the table to this graph here and to that graph right there, I see, again, let me plug in zeros undefined, 1, 2, 3, and 4. And the same thing here for the x values. Let's start with 0. It's going to be undefined. And then 1, 2, 3, and 4. I'm going to see again that these values up here are 1 unit higher, again, than the values that we have down here. So we see again a more direct correlation that the points that we have here are lower by 1 unit. Let me zoom in. Than these values up there on the orange one. So it makes it interesting again and how we can relate this to graphs and what type of transformation it is. So we have created, instead of visualizing as a horizontal dilation, we can visualize it as a vertical shift instead, which makes it easier to graph and get more information about the function itself. So let's now look at this example. So for this example, here we're multiplying 3 times, let me write this as the natural log of 3 times e to the second power. So I can expand it using, again, this technique. So the natural log of 3 plus the natural log of e to the second, which I can condense to the natural log of 3. And because, again, our property from the last section, we know that this property right here is going to just give us that exponent right there, that the natural log of e to the second is simply the exponent. So we can put plus 2. Similarly, with example D, this is the natural log. Well, I'm going to make 2 changes here. First, e times x to the 1/2. So instead of square roots, I'm going to use the equivalent notation, which means that the exponent of x is 1/2. So expanding this would be the natural log of e plus the natural log of x to the 1/2. And again, as before, this right here simplifies to 1. So 1 plus the natural log of x to 1/2. So we can think about this function here as simply this function shifted 1 unit high. Those two things are going to give me the same graph. Now the other usefulness of this function is that we can go in the opposite direction, that if I'm adding 2 logs that have the exact same base, I can condense this to 1 log by multiplying again the input values of each independent log. So for example, in example 2, in this example right here, since I have the common log of 5x to the second and I'm adding another common log of 4x to the third, I can simplify this as 1 common log. So I can write this as 1 log base 10. And all I have to do is simply multiply the two input values. So I can multiply the 5x squared with the 4x to the third, which condenses this into 20 x to the 5th power. Remember your exponent rules, that if I have x to a power and I multiply another x to another power, I simplify that by adding those exponents. So 2 plus 3 is going to give me this value of 5. And then 5 times 4, well, that's just going to be 20. And again, regardless of what the base is, I just need to make sure that the base that I'm adding, the log that I'm adding together, have the exact same base. So here, we're going to write 1 log and multiply 3x to the 4th with 7x to the 5th. Which is 21x to the 9th power. So for this example here, again, these are the same logs, natural logs. So I can condense this to one natural log by multiplying x to the first, y to the second with x to the third and y to the first. So this is going to become x to the fourth and y to the third. So 1 plus 3 is how I get that 4. And then 2 plus 1 is how I get that 2 or 3. And then for this example, the same thing. So I could write this as the natural log of x times 3x to the fourth, which is 3x to the fifth power. Now, this technique is going to be a lot more useful when we get to the section about solving equations. So we'll go back to it again. We'll go back to this rule, this technique in a section later on in this module. Now, the next property is called the quotient property. The quotient property, pretty much like the product property, has a log base b, and it's going to divide. It's going to be the quotient, so meaning that we're going to divide two things. This is going to be the difference of the logarithms. So difference, meaning that we're going to subtract them. So we're going to write this as the log base b of this value of m minus the log base b of the value of the denominator. Which, if we want to make a correlation to exponential properties, that would be this property right here, that if I have an x to a power and I divide it by another x to a power, then I'm subtracting again those exponents. Pretty much what I'm doing here, but with logs. So let's see how this works. So for this example here, in example 3a, since I'm dividing these two quantities, I'm going to expand this by getting 2 logs base 7. So I have a log base 7 of 19, and I'm going to subtract the log base 7 of the denominator x. Now the order of this is very, very important. This is not going to be backwards. This is not the same thing as the log base 7 of x minus the log base 7 of 19. That would be incorrect. It always has to subtract the numerator by the denominator in that scenario. So for this example here, to expand this, this would be the natural log of e to the third power minus the natural log of 7. And we could simplify this again. We didn't do that on the previous one because I wanted to write this underneath. Well, actually, we can't simplify anything there. But on this example, we can't, because the natural log and e are inverses to each other. Remember, this property is going to just leave us the exponent. So this would be 3 minus the natural log of 7. So again, let me demonstrate again the usefulness of this, of knowing how to use this property. So we should be familiar that the natural log of x, again, is going to have the x-intercept right here at 1, and that at e, which is that at e, because the base is e, the point e1 is going to be, again, a point that's on the graph, right? So that point right there. Well, if we just try to focus on this transformation up here, again, getting x here and trying to graph this might be a little bit difficult if we don't understand, again, how horizontal dilations are going to affect the graph. But if we rewrite this by expanding this, we create an equivalent form of this function up here. So let me hide all these points that we don't need right there. And we create an equivalent form of this function here by writing that one. So it looks exactly like that. Well, how does that compare again to the original function? Well, notice that first of all, it's upside down. It's been flipped and it's been shifted 3 units upwards. So this point here, our x-intercept, has been flipped across the x-axis, which is going to stay at 1, 0. but moved up 3 units, 1, 2, 3, puts that point right here at 3, at 1, I'm sorry, 1, 3, at that position right there. And then this point here, which is at E1, that has also been flipped upside down, so move down to, sorry, I'm trying to put my parentheses, negative E1. Sorry, E negative 1, wrong reflection, E negative 1, you see there, and has been shifted upwards 3 units. So if I add 3 units to that, so plus 3, it puts it up there. So it gives us the ability again to graph these more complicated log functions into something a lot easier because we've practiced again reflections, we've practiced translation, shifting things up and down, and why we didn't focus on the dilations because I knew this was going to come. We didn't have to worry about what's going to come into this next section. We didn't have to worry about, again, try to figure out, okay, what's happening horizontally when I do these horizontal stretches or shrinks. I can simply translate it and transform it into a vertical shift, and in this case, a horizontal, sorry, a vertical reflection, a vertical reflection flipped upside down, where I can then transform and graph the function as a result, which again gives me a lot more helpful information about the function itself than trying to work with this one up there. So now let's look at this example. So for this example, we're going to expand this to log base 2 of the number 32 plus, I'm sorry, minus the log base 2 of x to the third power. And well, this again can give us that value. There is a number, an exponent of 2, that could give us 32. And that number is going to be 5. If I multiply 2 times 2, 5 2s, multiply 5 2s, that does equal to 35. This is going to be 4. These two pairs is going to be 4. Oh no, it's going to be 6 because I need another 2. And these two are going to be another 4. So, no, I was correct. That was 5. 1, 2, 3, 4, 5. So this is 4, this is 4, which is 16. And that answer is 16 times the last 2, that's going to give you 32. So this can be simplified 5 minus log base 2 of x to the third power. So this is your condensed form, which is doing again two things. It's reflecting the graph of log base 2, well, log base 2 of x to the third power upside down, and then shifting it up because it's positive, shifting it up 5. So it gives us a good transformation of this thing instead of trying to figure out, again, what is that going to do to the graph. And for this example, this would be the natural log of 3x plus 7 minus the natural log of x. Now we can also go backwards. So if I am subtracting two logs, as long again as the bases are the same, I can condense this to one single log by dividing again these two quantities. So remember again, this is biconditional. Not only can I write something that looks like this to this over here, but I can write something that looks like that into that. So let's look at the next examples at the bottom of this page. So for this example, I can condense this. Since I have the same natural log, again, log base e, so the same thing, I can divide these quantities here. I could divide this by that. So I can write this as the natural log of xy to the fourth divided by x to the fifth, y to the first, which I can now apply my exponent rules to simplify that part inside there. So this would be the natural log of x to the negative 4 power 1. I'm going to write that rule right here. If I have x to a power divided by x to another power, that subtracts those powers. So 1 minus 4 is negative 4, and 4 minus 1 is 3. So here is your solution. So for this example, I can write this as the log base 3, not natural log, log base 3 of 5x to the ninth divided by 15x to the seventh. I'm just going to now simplify that. Well, 15 divided by 9, that equals to a fraction. That is not 3, it's 1/3. We can reduce that by dividing both those by a common factor of 5. And we can divide the x's by subtracting those exponents, which is x to the second power. So there's your answer. Now there's another notation that people usually write in this one. In this particular example, instead of putting the x over here on the left, to the right of the 1/3, you can move it as in the exponent and multiply the 1 with the x squared, because that's technically how you multiply a fraction with a whole number. You multiply the numerator of the fraction with the whole number itself. So 1 times x to the second is 1x to the second divided by 3. So this is another notation for the same, and again, it's an equivalent form, and you don't have to write it like this, but just thought I'd show you that these two things are the same and explain why. So moving along to the next example, this would be the common log of 12x to the fifth divided by 2x, which does reduce to, well, 12 divided by 2, that's 6. And x to the fifth divided by x to the first, that's going to be x to the fourth. So there is your condensed form to that format up there. And then lastly, this one right here, natural log of 16x to the third minus the natural log of 8x to the seventh. This would be the natural log of 16x to the third divided by 8x to the seventh, which gives me, first of all, 16 divided by 8, that's 2. But x to the third divided by x to the seventh, that's x to the negative fourth. And I didn't do this on the first example, but since we have a negative exponent right here, x to the negative fourth power, remember that there is a property that deals with negative exponents. That if a variable or anything, any base is raised to a negative exponent, I simply need to get the reciprocal of that, and that changes the exponent to a positive value. Most books write it like this, 1 over x, and then it has the power of n like that. But that's the same thing as this notation here, so we're going to use this notation there instead of this one, because we already have parentheses, we don't use too many. So I can write this as the natural log of 2 times 1 over x, and that changes the negative exponent of 4 to a positive exponent of 4. And if I follow the same rule that I mentioned in the previous one up here, this one right here, on how to multiply a fraction with a whole number, I can do the same thing. So to multiply this fraction with this whole number, I simply multiply the numerator of the fraction with the whole number. So 1 times 2 is 2, and therefore I can write this as 2 times x over, to the fourth power. So this would be another equivalent form as well. Now this concludes the first part, 2 properties of logs. I hope this was helpful, and I appreciate you watching, and I hope you have a great day.